Sometimes when we're doing linear regression problems, we might not have the actual data, and they might give us information, just some summary statistics, and we have to use formulas. And these formulas are on your formula sheet that I gave you, the yellow paper, which tells me that there's a chance that you might need them on the AP exam because they are made available to you. So the format for linear regression, and they use the same format as what's in on your calculator. So that's what this y hat equals a plus bx. So this is the regression equation. Now notice that you might look and say, well, what's the difference here? I still see this a plus bx. What this tells you is if you were to take all the means of the of the whatever your explanatory data is, I don't mean all the means. If you were to find the mean of your explanatory data and find the mean of your response data, though that point, x bar, y bar, is on the regression line. So that's what this is telling you, that this is actually, and I think that might be a question on your reading guide. This value, remember what R stands for? This is the correlation coefficient. The good news is I've never seen an instance where you have to use this formula. However, notice that it uses x bar, it uses the mean for both x values and y values to calculate it, which is why that the correlation coefficient is non-resistant to outliers. And that's because so is the mean. It's affected by outliers, so will be the correlation coefficient. And this right here, notice B is the slope. So this is the slope. This R is the same as the correlation coefficient, and this is the standard deviation of all your response variable data and the standard deviation of your explanatory. So, that's kind of helps you with those formulas, and we're going to do some problems with that. So this is number 1 from your textbook, and the only downside is that our textbook is older, and the formula sheet used to have b naught plus b1x, so I'm kind of glad that they actually made this a little bit better, matching the calculators. So so I'm just going to think of this as a plus bx. Okay, so just when you're doing a problem like that, just be aware of that. So in this particular problem, they tell me the means for both, I have x bar and y bar, I have the standard deviations for both the explanatory and the response, and I have the value of r. So I have to come up with my equation here. So notice that I don't know the slope or the y-intercept, so I have to figure that out. So I'm going to start by figuring out the slope for part A. Because I know I'm going to use this formula right here, and I can fill in. I know that R is 0.5, and I know that S sub y is 3, and S sub x is 2. So I get 1/2 times 3/2, so we get 3/4. So my slope is 3/4, and now I have to find the value of A. Well, this formula right here is going to help me because I know everything else. So you want to try and find a formula that you know everything except one thing. So I know y bar is 20. I don't know A. I know B is 3/4, and I know x bar is 10. So I can cancel a little bit here. So we have 20 equals A plus 15/2, and honestly, we can use our calculators. So we get 40/2 minus 15/2 is 25/2. So I have, now I can build my equation, y hat equals 25/2 plus 3/4 times x. And it's also fine, you can use your calculator and just have y hat equals 12.5 plus 0.75x. I mean, you might see it that way anyway. Okay, so next problem. We've got the same kind of setup, so we would do that the same way for part B. So you're going to have, as a matter of fact, I'm going to pause and go through it because it really is the same setup. Okay, so I went ahead and just worked it out. So I used the same formula. So we have R is negative 0.4. Then you're going to take your value of S sub y over S sub x. So I'm just using my formula to find the slope, and I got negative 8. Then I used this formula here and filled in what I knew and solved for A and got 23.2, and then I just built the equation. Now notice in this one we have no context. This is just an exercise on how to use the formulas. All right, so let's take a look at part C. So it's a little different because we got something else that's blank, but this time they give me this value here. So what does that tell me? I know that the value of A is 200, and I know that B is negative 4. So I know that A is 200 and B is negative 4. I know the y-intercept and the slope. So if I know that information, I know the slope, so what else do we know? We know R. We don't know S sub y, we know S sub x. I know x bar, so I think this is where I want to go next. If I don't know y hat or y bar, but I know A is 200, and I know B is negative 4, and I know x bar is 12. Okay, so we could solve that using my calculator. I guess I could have pulled up my other calculator there. So I get 152. So that is, I'll fill this in here. And now I need to find S sub y. I know B, I know R, I know S sub x. Okay, so we know B is negative 4. We know R is negative 0.8. I know S sub y, I don't know S sub y. But I know S sub x is 6. So I'm solving this. So I'm going to multiply both sides by 6, so I get a negative 24, and then I'm going to have to divide by a negative 0.8, and I get S sub y equals 30, so I could fill that in. And we were just asked to fill in the chart. I guess I could have filled those in up there, but so that's part C. And then part D, I'm missing R, but I know S sub y and S sub x, and I know B because we have A and B right here. So I'm going to solve for R by filling this in. So B is 50, and I don't know R, but S sub y is 100, S sub x is 1.2. So now I'm going to multiply the 50 times 1.2 and divide by 100, and I get R is 0.6. Okay, so R is 0.6. I'll go ahead and fill that in. And now I need Y bar. So I think I know everything else. So Y bar is A, which is negative 100, plus B, which is 50, times X bar, which is 2.5. So I get 25. So I would fill that in here. So that's what you're going to do on a similar problem. All right, on the last video, I talked a little bit about residuals and what you're looking for in a residual plot. So remember that when you are looking at a residual plot, you don't want to see a pattern, okay? If the actual data if a linear model is appropriate, then the residuals should not show a pattern. So this one in part A shows no pattern. So this tells me that a linear model is appropriate. Now, it might not be accurate, and well, we'll have to talk about that probably in class, the difference between saying something is accurate and something is appropriate. But a linear model is appropriate if the residual plot shows no apparent pattern. This one, clearly there is a pattern. I mean, you can kind of see they go up, they come back down. So because the residuals are showing a pattern, a linear model is not appropriate. You don't have to know at this point what kind of model is appropriate. We'll investigate some nonlinear models later, but right now you just need to know if a residual plot shows a pattern to it, then a linear model is not appropriate for that data. Here, this kind of has like a fan pattern. It's still a pattern though. So notice that I can predict some things about the next residuals. I would think that they're probably going to continue this kind of opening, this fan pattern. And because I can make predictions about it, that means there's a pattern. So because there's a pattern, a linear model is not appropriate. Okay, so you have to be able to tell that from a residual plot. The next question, and I think a series of questions are going to deal with this real estate problem. A random sample of records of sales of homes from February 15th to April 30th, 1993 from the files maintained by the Albuquerque Board of Realtors gives the price and size in square feet of 117 homes. A regression to predict price in thousands of dollars from size has an R squared, so R squared, and a lot of times you'll see this with a capital R, is 71.4%. And you might see it like that. Your calculator actually does it as 0.714. The residuals plot indicated that the linear model is appropriate. So that's a big deal, the fact that they tell us a linear model is appropriate. Okay, so it tells us it's already been checked. So part A is asking, what are the variables and the units in this regression? So the explanatory variable So you think about what you're predicting. They are saying that they're predicting price. Well, that makes price the response from size. So the explanatory variable is size, and it is in square feet. The response variable is price, and that is in thousands of dollars. All right, so part B. What units does the slope have? Well, think about your rate of change. It's the change in y over the change in x, going back to algebra. So it is the change in the response variable. So it's going to be price, thousands of dollars per square foot. Per. All right, so part C says, do you think the slope is positive or negative? Okay, well, let's think about it. Think about as the size of the house increases, what do you expect the price to do? Well, you'd expect it to increase. So it's probably positive as the size of house increases, we expect the cost to increase. Okay, so that takes care of number 7. Number 9, real estate again, so still with the real estate idea. The regression of price on size of homes in Albuquerque had an R-squared value of 71.4% as described in exercise 7. Write a sentence in context summarizing what the R-squared says about this regression. Okay, remember what R-squared is. This is called my coefficient of determination. And remember the little thing I gave you, kind of a fill in the blank. So it tells us 71.4% of the variation in response variable, so that is the price. So 71.4% of the variation in housing cost. And I'm going to put thousands of dollars in parentheses. So 71.4% of the variation in housing cost can be explained by the changes in square footage. And that kind of implies size. I didn't use the word size. I could have said it can be explained by the changes in size, and then I could have put in parentheses square footage, but I think that it is implied there. So again, r squared, you put the r squared value here, of the variation in response variable, goes here, can be explained by the changes in explanatory variable. So almost like a little fill in the blank. Notice now, do you have to use the word variation and changes? What if you said 71.4% of the changes? And, I use two different words, just makes it sound a little better. But this is the idea that you need to convey for r squared. Okay, next question. Still on real estate. The regression of price on size of homes in Albuquerque had r squared equal 71.4% as described in exercise 7. What is the correlation? Well, remember the correlation is r. So you might wonder, we know r squared. How do we get r? It is that easy. You actually are just, if I can get the pen tool here though again. You're just going to take the square root of whatever r squared is. So we want the square root of 0.714 and I get 0.844. We'll just go 0.84. That's fine. Okay, so there we go. Part B. What would you, now we can talk about how strong that is. Okay, this is fairly strong. Notice again, I still say things like, it's not, I wouldn't say very strong, like if it was like 0.98 or something, but it's fairly strong. What would you predict about the price of a home, one standard deviation above average in size? If you look on page 171 in your textbook, there is a little formula that they give you that tells you this relationship. If you standardize your response variable and your explanatory variable, then you get this relationship here. Not on the formula sheet, but we do have this relationship here. So when you look at this, what would you predict about the price of a home, one standard deviation above average in size? So what they're telling you right here is that your z sub x is 1. And we already know r. So if I wanted to know about my price, then I could take r, which is 0.84, times 1, which obviously is 0.84. So that tells me that the price would be, the price is about 0.84 standard deviations, and it's positive, so it would be above average. In I guess I don't need the in there. I kind of said it. All right. So part C. What would you predict about the price of a home, 2 standard deviations below average? So I need to fill this in. R is 0.84, and now the Z would be -2 because it's 2 standard deviations. So if I take 0.84 times 2, so it's going to be a -1.68. So that means that the home would be about, the house is about 1.68 standard deviations below average or below the mean price. Okay, the house is about 1.68 standard deviations below the mean price. So that's what you would do there. Okay, so the last problem, still real estate. Consider the Albuquerque home sales from exercise 7. The regression analysis gives us this model. So now we're told, now notice how they use words like I've talked about. So price hat, so that's my predicted price, equals 47.82 plus 0.061 size. So that's my explanatory. Explain what the slope of the line says about housing prices and house size. So remember how you're going to interpret slope as the size increases by 1 square foot. The model predicts if I could spell correctly. So as the size increases by 1 square foot, the model predicts the price of the house to increase, to positive slope, by about, now let's think about this. This is 0.061 thousands of dollars, remember, per square foot. That's a little awkward. So to say by about 0.061 thousands of dollars. Instead, if I wanted to just change this to dollars, it's thousands, so I would have to go like this. So I could say by about $61. So it's about $61 per square foot, which is a little, if you said 0.061, but you can't say $0.061 because that would be wrong. So if you would have to say 0.061 thousands of dollars. So it just kind of makes a little bit more sense, I think, to say that. So for part B, what price would you predict for a 3,000 square foot house in this market? Okay, well, you're going to just substitute in for size, 3,000. So we get price hat, which is our predicted price, equals 47.82 plus 0.061 times 3,000. So I get, now remember this is thousands of dollars, so 230,820. Because remember this value, if we left it as obviously if you said $230.82, you are not using very much common sense there or number sense, because obviously a house is not going to cost that. So you would need to make sure, oh yeah, that's in thousands of dollars. So if we move the decimal point 3 places, then we would have what that cost would be. So a real estate agent shows a potential buyer a 1,200 square foot home, saying that the asking price is $6,000 less than what one would expect to pay for a house of this size. What is the asking price, and what is the $6,000 called? So excuse me if I'm repeating myself, but I had paused the video and now I'm not quite sure. Anyway, so here's our regression line, or regression equation. What I did is I substituted in a 1200 so I could figure out what the predicted price would be. So my model predicts the price of a 1,200 square foot home would be $121,020. But if it was advertised the asking price is $6,000 less than that, then the asking price would be $115,020. But then they ask you, what is that $6,000 called? Okay, so remember one of the things I talked about was to get the residual, you take the observed minus the expected. So the observed would be the 1,000 or the $115,020 because that's what is really being asked. The expected would be $121,020. Notice that if I subtract these in this order, I get negative 6,000, and that is actually the residual. It's the difference between the observed minus the expected. Notice it's a negative residual because our asking price, our observed, is less than what's expected. So that should take you through the examples that you would need to know in order to do the homework that I have assigned.